Well, we're now going to move from North America to South America, and hopefully the connection will work. So our next speaker is Jonathan Barichivich, who did his PhD in CRU from about 2010 to 2014, and Keith Briffa supervised him. And I hope he's there in Chile. Hope this connection works, Jonathan. And Jonathan's going to be also looking at tree ring data and how they might improve global vegetation models. And Jonathan has recently been awarded one of the ERC starter grants, which are quite competitive, and he should be starting that fairly soon in Paris. So you can start, Jonathan.
Hello, everyone. I managed to get here in a bit improvised office, but I'm very happy to be here, and I will show you some of the work that I am doing now, and as part of my ERC grant as well. So I have this work in collaboration with colleagues from the LSE in Paris, and also from Holland, Sebastian Lysard and Gina Jeong, our PhD student. And I did my MSc and PhD in CRU with Keith and Phil and Tim, and now I am associate fellow at CRU. And I was the last student of Keith. I'm very proud of that, and I'm very sad that he left us so soon. And in a way, most of the work I have been doing now, it's been back to tree rings, and I think he has been a main inspiration in this part. And so for this talk, I will talk to you about the uncertain response of the terrestrial ecology in Earth system models. And then I will show you what we can get from tree rings to improve the ecology in these large scale models. And I will finish showing you in a rather conceptual way how we will push the field to integrate tree rings and these models. And just to start with some conceptual ground, so an Earth system model has different models inside, and it has one atmospheric model that simulates all the atmospheric dynamics, and has another big model which is the ocean dynamics. So it's an ocean model, and then all what happened on land, which is involved all the terrestrial ecology in the Earth system model is done in the land surface model component. And so, for instance, here is the IPSL Climate Model 6, is the latest version of the IPSL, the French Earth system model, which I worked with. And the atmospheric model is called LMDZ, and the ocean model is NEMO. And then the land surface model is ORCIDE. So I will be today talking to you of the work that we are doing to improve ORCIDE. So to improve the terrestrial ecology component in the Earth system model. And the terrestrial ecology has the terrestrial biosphere and also the ocean biosphere, but the terrestrial biosphere has very important role on the speed of climate change currently, and also it has very important feedbacks to climate, being because of the carbon cycle, the water cycle, and all the energy cycle. So these models are taken here. The Earth is divided in grid boxes, and then over the land surface we divide a grid box within different type of vegetations, and then the ORCIDE model simulates the exchange of water, energy, and also trends in vegetation between these vegetation fractions and the climate and the atmosphere, and feedback to the climate. So this model are used to monitor trends in biogeochemical cycles, or carbon, water, and energy, and vegetation as well. And also with these models, we can attribute the causes of the trends that we observe, the historical trends, and also the variability. And more importantly, these models allow us to predict future changes of the terrestrial biosphere under new climates and emission pathways towards the future. These models are also known as dynamic global vegetation models, but we call it more land surface models. So this model is key to climate projections, the terrestrial component, and it's a key component also of the latest IPCC report and the magnitude of climate change that we are going to have in the future in a range of Earth system models, which are about 15 or 20 models and different versions. So the problem that all these terrestrial component of land surface models, then when we project the change in carbon towards the future and the different climate scenarios, here there is one scenario. So from 2000 to 2000 to the end of the 21st century, we see that the terrestrial component, the land, it's very uncertain. So the range of the projection goes from what we say a big source of carbon from the land to the atmosphere here in positive values, or a sink of the carbon from the atmosphere to the land. And these uncertainties, if we compare with the oceans, it's 3 to 4 times higher on land. And this has been an issue that has been sticking around for the last 30 years of development of these land surface models and Earth system modeling. So this is a very big problem, because this feedback, the amount of carbon in the atmosphere is proportional to the amount of warming in the future. So we get a very different range of outcome of climate if we have these different carbon cycles. So this is a big problem, and then part of these uncertainties is it comes from model structure, from parameters, and also drivers from the historical period when we run for the 20th century. And in the model structure, there is one very key assumption in this model, is that biomass growth, we take carbon through photosynthesis and then we convert it to biomass, but that occurs by magic. So it's a biomass growth in this model's current generation of land surface model is a direct dependency on photosynthesis. So we call this is the source-driven growth paradigm. And this has been criticized by ecologists like Christian Kerner groups, and it's a major problem in how we convert carbon from the atmosphere to sequestrate it to the biomass in forest. And then there is another problem which goes for the parameters, is that there is a lack of long-term constraints, benchmarks. There is currently no benchmark for the whole 20th century, for instance. And so under this current situation, where we end up with this very huge uncertainty in projection of the carbon cycle to the future, we calibrate the model over 30 years, 10 to 20 or 30 years, which are satellite observations, ecosystem measurements like FluxNet of eddy flux towers, and some ecosystem experiments that they barely are overcome 30 years of length. And then we calibrate our models, our land surface model over these 30 years, and we project to the future, and we get a very wide range of answers. And as Jessica was pointing out earlier, we are putting the rule of the game over a very short period, and where the CO2 has increased rapidly, but in a very short period. We don't have the gradient of increasing CO2 in this calibration of this model. So they lack that. And so here, more in a perspective from here is a time Turing series in green, and in blue the CO2 concentration. So we see here from 1500 to 2000, we see the rapid increase in CO2, which is about from pre-industrial to is about 35% or 40% until now. And then we see also the response of true rings over the same time scale. And then we see here like other data that are used to calibrate this model, like phase experiments, which are 10 years more at the most, eddy covariance, which are 20 or 30 years, but most are 20 years, and satellite observations and some forest inventories that capture a bit more of the grain. But true rings really bridge the pre-industrial to current situation of global change, especially increasing CO2. And they are widely distributed over most of the temperate and boreal regions. And then our premise is that true rings can help to constrain the biomass production and transpiration or stomatal responses in our simulated vegetation at long time scales from pre-industrial times. So the true ring capture this grain in contrast to these short-term ecosystem observations. But there is a problem. Using true rings in this way, which has been collected to reconstruct climate, and we know most of the treatment as well, the methodological issues that there are and the workarounds that, like Ed was showing, are usually for climate reconstruction applications. So for ecological applications, we have to face some challenges. And in general, in the global change community, there is a very negative view towards using true rings to reconstruct past forest growth or to reconstruct physiological changes. So here is, for instance, a comment of a reviewer in one of our recent works, and skeptical, that says that we acknowledge the general difficulty of disentangling multiple climatic and biological influences on true ring growth data. This challenge their use within this type of research to improve models. So here is where these biological and climatic signals combine. It's very difficult to disentangle them, as the reviewer says. It's a challenge. And here, for instance, to illustrate this, here there is like a cube where on one side we have the global change factors, increasing the nitrogen deposition, increasing CO2 depositions over the 20th century, and increasing drought severity and frequency, VPD, temperature. So multiple factors that are increasing together. And then we see how those climatic factors or global change factors affect the processes to climate, microclimate, then to photosynthesis, then to allocation and carbon storage, and then to xylogenesis, which is wood formation, and then how a true ring is formed. And then we pass through all these processes that Hal Fritz conceptualized very, very early in the 70s. And then, so these processes are a filter for these global change factors and result in trends in true ring parameters that we have to interpret in a way. So, for instance, there is a tendency for decreasing wood density over the 20th century, and ring width in many places doesn't change at all in a clear trend, or the trends are very, very uncertain. And then there is also a clear increase in growth synchronicity since after the 70s. And also there is an increasing water use efficiency in isotopes, but then that increase has been, the rate of that increase has been slowing down over the past decade or so. So to understand this process and disentangle the influence of these factors, we have to understand what what produce tree rings. And that I call physiological dendrochronology. And that is an innovation of the work that we are doing in a way. And that is done in monitoring sites where we need to have together different type of observations to really interpret tree rings and then to be able to model them. And currently, in land surface models, there is only one land surface model that simulates, or two more or less, that simulate some Turing variables explicitly. So we have the Orchid model, where we simulate the oxygen isotope, stable isotope in the Turing in wood, carbon, and tree ring width or radial growth from radial increment, from stem radial increment. And this is the current situation, the best we have in a way in terms of model and Turing data. And we can use this Turing data to calibrate this model or to benchmark the model, but we might get the right answer for the wrong reason if we tune the parameters, because this model currently is all the biomass growth is just directly from photosynthesis and carbohydrate allocation. So it does not have wood formation or phylogenesis process, which has different environmental sensitivities. And this work has been published recently in Biogeoscience and also in GMD, Geoscientific Model Development, where we were able to have a model that simulate these three parameters, which is Orchid. Then I argue that if we use physiological dendrochronology, which is this process of enhancing process-based understanding of Turing variables, and if we improve land surface model by including phylogenesis, so to have growth as a function of source and sink, as we call it, we can have the right answer for the right reason. And then we will have an Orchid with model that is enabled with phylogenesis, with formation. And then we will have Turing data, all the different type of Turing data that are available, including phylogenesis observations, really consistently for data model integration. So that's what is meant to be done in my ERC starting grant proposal, which is called CATES. And we have been piloting this physiological dendrochronology in a FluxNet site that I have here in southern Chile. And here, in order to use tree rings to improve models, we have to go conceptually to separate the different signals. And here I built on the aggregate tree ring model that Ed presented earlier on, where growth in a real tree ring is a function of source and sinks, so photosynthesis and wood formation. And that ring width will have a climatic signal, and then a size related trend, and endogenous disturbances sometimes, and exogenous disturbances and other times, and then some unexplained variability. So this is nature, and now we can mimic that at this time. We can mimic most of the signals, but still we have our model simulated ring width or radial increment just as a function of photosynthesis and carbon allocation. But then in the model, we do have a climate-driven growth, and we have also a size-dependent growth from allometry of the stem. We have within stand resource competition, we have the self-thinning rule, and we have also forest management in the model. And then we have natural and anthropogenic disturbances. For instance, here it will be like the changing nitrogen cycle, or changing CO2 concentrations, well, CO2 fertilization, for instance, and then some model errors and accounting processes. So, but still there is the inconsistency that we miss here the process of wood formation or the process of carbon sink. So this current version of Orchidea has a photosynthesis model, which is the Farquhar, very common model used in most of land surface model, with some both very stomatal conductance. So here photosynthesis, stomatal conductance, and internal CO2 concentration in the leaf. So ring weight is simulated from just radial circumference from stem increment from GRT minus this year minus the previous year increment, and then we have a very simple model for carbon isotope discrimination, and then oxygen isotope in the Turing cellulose, which involve a fraction of the isotopic signature from source water, and then from what happened in the leaf with leaf enrichment with the transpiration and other processes, and then some other component what happened, the change between the two signals when it goes to cellulose. So very simple. And the second line of development that we have been doing is combining growth and physiology in the same Turing. So for instance, typically we have a Turing width time series, we have isotopes, carbon and oxygen separately, and we do analyze them, and at the best there is the dual isotope approach to constrain physiology, leaf physiology, but it's usually not easily linked to growth. So here we devise, in this recent publication, we devise the Turing triplet. So where we, in one axis, we have in the bottom axis, we have the isotope, the oxygen isotopic composition of cellulose, and also the Turing discrimination in the other axis, and then how leaf stomata respond to this combination of factors and environmental drivers. So here is the stomatal conductance. It's a key variable that increases when we move to this side of the cube, and then in the vertical we have the growth, and then here we can, for instance, link individual years, and when we fit a surface and to see the overall pattern of linking growth and physiology. And for instance, here 1976, this is for France in Fontainebleau forest oak. It was a very narrow ring. It was a very narrow ring. It was very enriched in oxygen, and it had a very low carbon discrimination, which is a response to drought. And so the stomata were closed at that period, and vice versa. You can go with very probably wet years, and then you see good growth, and low, you have much more open stomata. And this device allows us to interpret growth variability much better. And here, for instance, we get the classical view where we compare a model with observations in black for ring width, one model in red, Orchidea, and also another Turing model made in ISO in gray. So then we can combine the three things, and we get the response surface, the physiological response surface for the model, and then we can compare it with the observation. So for instance, here we see very different response surface for the models, and Orchidea tend to be more consistent with the observations than made in ISO. Despite that, made in ISO tend to perform better in some individual parameters and has been tuned with a Bayesian calibration. And a third line of work, it's been to look below ground and to devise a below ground Turing perspective. And this is done by also coding coarse roots, and the stem of the same tree. Here, for instance, we have a view for the last 50 years or 70 years of growth in the stem and in the root. And then, so the decadal trends are very different in the two organs, and the internal variability tend to be in phase, but there are some periods where they are anti-correlated or they are not in phase. And also, this can also be done internally by placing dendrometers. Here, this is a 1 month worth of observations, and this is the radial size variation in red of the stem and in black of the root. These are daily cycle. On top is the vapor pressure deficit. So the tree shrinks when there is the atmosphere is drier. And we see that the trends, the accumulation of the growth, this is peak growing season in the Southern Hemisphere, are quite different in the two organs as well. So there are differences between stem and roots, and that tell us something about allocation, growth allocation. And another improvement that we have been doing in order to exploit tree rings, it's been to combine flux towers and tree rings in the same site. So here is our flux net in a coniferous rainforest in southern Chile. And this is the annual cycle of net carbon uptake. Most of the uptake is in spring, and then towards the summer, the uptake is reduced because of drought stress. But then we see that the wood formation, when we look at the cell by cell growth, the peak is in 21st of December, the peak wood formation or cell division. And then the cell maturation and enlargement, and when carbon is being deposited in the wood, it occurs 1 month later, and the phenology is different than the carbon uptake. But we can increase our physiological understanding by having a flux tower right there, and these measurements are being done in the footprint of the flux tower. And so with all these devices, then we put together this ERC starting grant, which is called CATES, and is about long-term consequence of altered tree growth and physiology in the air system. So this will go from from this year until 2027, 5 years. And I have a team of 5 persons and 1.5 million euro to tackle this challenge of using tree rings to reduce uncertainty in projection of the carbon cycle. So as we go back here, we see that the current situation, we have the long-term increase in CO2 over the 20th century and toward the future, very uncertain projections and a small period for calibration. And then I argue that we can match the scale of global change if we use tree rings for the whole 20th century to constrain growth and water use efficiency. And this is done by combining tree rings and FluxNet data. So here we have we can with tree rings or the ITRDB or specialized sites, we can go back beyond 100 years. And then another very important factor to reach this is that we will open the book of tree rings. We will go beyond ring width and use phylogenesis observations that now some are multi-year, 5 to 6 year, or even 10 years in some sites, that tell us about biomass growth, of the process of biomass growth. And then we have also isotopes, which are about 700 sites probably in total globally, that will tell us about water use efficiency and leaf physiology over the 20th century. And then we will have some root rings in some sites to constrain carbon allocation changes over the 20th century as well. And these multiple constraints should really help us to put error bars to the 20th century and to constrain these processes together. And sorry, this multiple constraint. So, and then with all this, we will be able to use the past to constrain the future sensitivity and eventually reduce the uncertainty range in our projection of the carbon cycle response to climate change. And so to reach this, we need a full data model integrations, and this means moving from this current situation where we have a source-driven growth paradigm to an integrated source and sink growth paradigm in the next generation of land surface model. And ORCID should be the first model, global model, and have all both the isotopes and ring width, and also by the phylogenesis processes. It will mean that we put a process between photosynthesis and biomass, with biomass growth, and that will be wood formation. So now it's just converted, carbon is converted by magic to wood formation. Now it will be converted by phylogenesis. And so the panel really saw that this work could really improve the representation of forest growth in Earth system models, and it could have potential important impacts on the global carbon cycle uncertainties. So this is a high risk, high gain work, and we expect that it will will produce a game change in model evaluation. So the environmental sensitivity will go from just 3 decades of calibration to a whole century. And then that should result in uncertainty reduction in the future land sink carbon projections by up to a third, probably, because it will be one component of the terrestrial ecology that will be improving to improve growth biology. And then it will also produce a conceptual advance, which I call physiological dendrochronology, which is combining different Turing parameters and combining them also in supersites in the same place, because now they are spread over different places and they are not collocated. And this should also result in new data sets. So I will push for a global network of stem and root chronologies aimed to capture this allocation and below ground for responses to 20th century climate. And also here is an important bridge. I want to test if the growth of coarse root can tell us something about the fine root mass growth as well. And so that would be is the big challenge, and that involve uncertainties and also methodological issues, and also going beyond ring width. And with this, I will end my talk, and there is my contact, and thanks for your attention.
Thank you, Jonathan. Do we have any questions in the audience? Yeah, go ahead. You get the microphone first.
How comparable are the models for terrestrial and for temperate and tropical forest? Because I did work on tropical wood rings, and it's, believe me, it's way different from what you have in the tropics.
Yes, that's a very, very important point. And so what happened here is that if we there are some true rings in the tropic, but not too many. But the important thing here will be the process of wood formation that will operate everywhere in different biomes. And this will, there is the biomass mission that is being launched by ESA now, probably this year, and it will run along the project. So I would expect a very high resolutions satellite product of biomass growth at about 300 meter resolution probably, and high temporal resolution too. So if I have the process wood formation, I would also be able to assimilate this satellite data together with true rings to fill that gap that are in true rings in the tropics. That's the hope for the tropics.
Okay, do we have any online questions? Okay, go ahead.
So this question is from Oliver Nelly. Thanks for the great talk. How do you deal with human management influence on xylogenesis for your 100+ years data set, disentangling from climate influence?
So first, xylogenesis data at most are for 10 years and for very few sites. And again, the important thing is to have the process of wood formation, and then I would, and those sites where we have xylogenesis usually are not disturbed by forest management. And forest management, so with having this process and then calibrated with these short multi-year observations, hopefully at the same time where I have a flax tower, I can really close the carbon cycle, let's say. And then, so I have the process of information, I calibrate it with this observation, then I can simulate for the 21st century what would be the growth, or the ring width for that site. And then I will have mismatches with the observation, which will be due to disturbance, for instance. But I will only be able to simulate the climate-driven part of ring width in that signal going back to the aggregate model.
Thank you, Jonathan. And I look forward to seeing you in the real world at some point when you get a chance to come to Norwich from Paris. Okay,
I will
thank
come
you.
to visit. Thank you.